Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, does it learn by doing? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and in today's episode, we're exploring two of the most important and rapidly developing fields in robotics: perception and manipulation. I'm finding out how smart robotic manipulators are tackling challenges ranging from improving medical care to disassembling electricals for recycling. Before that, I'd like to remind you to support the podcast by signing up as a paid supporter on Patreon. Not only will you receive my eternal gratitude for helping the podcast to continue, but you'll also get access to lots of cool perks, including monthly bonus episodes, behind-the-scenes updates, merch discounts, and more. Check out patreon.com/Claire Asher and join the Robot Talk community today. So, without further ado, it's time for me to introduce this week's guest. I recently had a wonderful conversation with Maria Koskinopoulou from Heriot-Watt University about autonomous robotic manipulators for surgery, industry, and beyond. Today, I'm chatting to Maria Koskinopoulou, an assistant professor in robotics and computer vision at Heriot-Watt University, researching robotic manipulation, perception, human-robot interaction, and machine learning. Hi Maria, great to have you on Robot Talk.
Hi Claire, thanks a lot for the invite. Very excited to be here.
So you co-lead the Autonomous Robotic Manipulation and Multi-Agent Systems Lab at Heriot-Watt University. So can you tell us a bit about the current research that's going on in your lab?
Absolutely. So here in our lab at the Heriot-Watt University, we focus on helping robots interact with the real world in more intelligent and adaptable ways. Our research combines, as you said, robotic manipulation, computer vision, AI, machine learning, with applications ranging from healthcare to sustainable manufacturing. One quite interesting and exciting area we work on currently is dexterous manipulation, essentially teaching robots how to grasp and handle objects more like humans do. That involves designing new robotic grippers and effectors that can manipulate delicate, complex, or unpredictable objects. And we are also doing a lot of work around robotic assembly and disassembly of electronic devices, which is becoming increasingly important for sustainability and recycling. For example, we can teach a robot to safely take apart a hard drive, a battery pack, or an electronic component that was originally designed for humans to assemble or disassemble. And these tasks are surprisingly difficult most of the times because every object is different, is varying among different devices. Screws are very, very small, are tiny. Objects sometimes are hidden. Materials are deformable, and the robots needs both perception and physical interaction in order to adapt and perform these kind of tasks in a meaningful way. That's mostly what we are doing. And
that's enough to keep you busy.
Exactly. And one more thing, and what I really enjoy in this research is that it's highly interdisciplinary, I would say.
Mm-hmm.
We bring together, different backgrounds and different expertise, like robotics, like programming, software, or hardware, like design and manufacturing, and this type of skills, AI, human and robot interaction, in order to solve real world problems that could have societal or environmental impact.
Mm-hmm. Yeah, I mean, we'll definitely come back to talking about the autonomous kind of disassembly and waste stuff later, because that's really cool. Talking more generally, dexterous manipulation is something that over the last year just seems to be popping up everywhere. Like, I've had quite a few guests on this season who are kind of doing things in that area. Obviously, it's quite a big umbrella. It seems to be quite a big research topic at the moment, and I guess it's really taking that step to allowing robots to be more generally useful in the world, right? To be able to interact with it effectively and precisely.
Yeah, exactly. And I'm glad you mentioned that. To be honest, it's not alone like dexterous manipulation, but it can be coupled quite well with perception, because without this type of, sensing capabilities, the robots alone cannot do extremely big things. And also the idea is that we need to have more dexterous manipulation in different type of applications, and enhance robots with adaptability and generalizability at the same time. So we don't want, to pre-program a robotic system in order to perform a task in a very known structured environment, but we want it to be able to learn a task here and then. I mean, learn how to disassemble a hard drive, for example, but being able to generalize this to a laptop, another PC, a desktop, and different other devices. So that's the case. And in this direction, as I said, like perception helps a lot. Other sensing capabilities like force sensing and others can help a lot to give this ability to robotic systems to be able to generalize their knowledge in unstructured and more challenging environments.
Yeah, I mean, when I was reading about your research, it struck me, seeing the kind of the perception and the manipulation together. And I thought, I don't often see that, people, and I don't want to disparage previous guests or anything like that, but, people will often say, I work on manipulation or I work on computer vision. And I haven't seen that many people who are combining the two. But when you think about it, they really go together hand in hand, because if you can't sense the world around you, you can't interact with it, effectively. Can you talk a bit more about how you integrate robot sensing and manipulation within your research?
Yeah, exactly. I totally agree with this, that they are going hand in hand, to be honest. So a robot needs to understand its environment before it can interact with it properly. And humans do it, and animals actually do it naturally. When we pick up a cup, for example, when we are performing another manipulation task, we instantly judge the position of the cup, the shape, the weight, maybe even whether it is fragile, if it's full of, liquid, water, coffee, or anything. So for robots, that's actually incredibly difficult. So we need to teach robots how to get all this information and act in a more intelligent way in their environment. So in our research, we try to tightly integrate perception and action rather than treating them as a separate problem. So instead of saying first the robot needs to see and then it acts, we think about it as a continuous feedback loop. So we are looking to real-time applications that vision and perception systems are always feeding up the manipulation tasks and the actions of the robots. So in the same context, actually, one thing that I find quite fascinating is that humans are incredibly adaptable, if you can think about it. So if an object slips, for example, from our hands, we immediately react without continuously thinking about it. So this is the goal also of our research, and this is where we envision robots to be at some point. So to be able to adapt in different conditions and interact in the same way or as closer as they can with humans.
Mm-hmm. Yeah, I mean, when the reason that humans have this ability to kind of see an object and know some of its properties and understand like how to go about picking it up, that's because we spend a lot of time as babies and toddlers kind of picking things up and trying it out and finding out what works and what doesn't and kind of learning about the world that way.
Exactly.
Is there an analogy for that with robots?
Yeah. Actually, this was the broader area of my PhD research. And there is quite a lot of research on learning from demonstration, as it's called, and especially as a bio-inspired topic. So, and there is a full analogy of how humans are learning gradually from the time that they are very young, like kids, by touching things, by mimicking the parents and their environment. And there is a full research that is called learning from demonstration that is based on the same principles and how robots can gradually learn from their environment, actually, and then acquire all these adaptability and generalizability skills.
Mm-hmm. And I guess that all comes back to perception again, because in order to do that learning, you have to be able to see what you're learning from. Maybe you have to have touch receptors in your hands or robot grippers or whatever, so you can feel the object and feel like, you know, the pressures, and yeah, it all kind of comes full circle.
Exactly. It's a closed-loop circle, to be honest, that one fits the other.
Mm-hmm. So, as you mentioned at the beginning, you apply this research to a lot of different areas, but one of the main ones you've been interested in is medical robotics. So, can you talk a little bit about some of the work you've done for medical applications?
Yeah, of course. So, medical robotics is one of the areas I'm most passionate about, obviously because of the impact that this can bring, that can be quite direct and very meaningful. So one of the projects I've worked on involves autonomous robotic system for needle-based medical procedures, like intravenous access, peripheral catheterization, thoracosynthesis, where fluid is removed from the area around the lungs.
Okay.
Or blood sampling, from the arm and catheter placement. And these procedures require high precision and are often guided using ultrasound imaging together with an external camera or other sensing technologies. And we developed a robotic system that combines ultrasound perception, robotic manipulation, and autonomous control for performing this type of operations. The robot can identify the target using imaging, position itself accurately, and assist with the needle insertion process. And what's really exciting, it's again the integration of sensing and physical interaction at the same time. Because the robot is not just moving blindly, it's continuously interacting with the environment, and we have a real-time feedback all the time, because especially in the human body, for example, the organs are moving. We breathe. All this can create small changes of the organs or the tissues that we target. So in that case, we need real-time feedback. So it's very important to have this coupling again. I'm also very interested in haptics and force feedback in this type of surgical applications, essentially giving robots a sense of touch, as we mentioned before. In minimal invasive procedures, surgeons often lose natural tactile feedback. So robotic systems that can restore or enhance that sensation could improve both precision and safety during these procedures.
Yeah.
And just to be clear here, the broader goal is not to replace clinicians, right? It's not to replace surgeons. It's just to support them, like enhance their awareness, as we used to say. So robotics can considerably help reduce like fatigue, improve consistency, enhance precision, which is very important, give another level of safety, and potentially make advanced healthcare more accessible in a lot of cases.
Yeah, the haptic one you were talking about with the surgical robot. So would that basically, the surgeon is teleoperating a surgical robot, and that robot is then feeling, whatever it's feeling, muscle or tissue or whatever inside the body, and then kind of relaying that information back as, I don't know, maybe a vibration for the surgeon or something like that?
You're good. Exactly. That's exactly what we do. So the surgeon teleoperates the robotic systems through some joysticks. You can imagine them, like we call them phantoms. And in these joysticks, the clinicians, the surgeons, can feel if there is an obstacle, maybe because of like a structure that comes up during the insertion of the needle, for example, or if there is a soft tissue, or if there is like, a blockage, liquid, a vibration, as you mentioned, like these different types of tissues and cases that we may have.
That's really cool. So we had a relevant audience question, which brings up, I think, a really important topic. So Jeremy on Twitter asked if you could address clinicians' concerns around autonomy versus supervision for medical robots.
Exactly. That's a very interesting question because I think there is sometimes a gap between public perception and what is actually happening in hospitals today, right?
Yeah.
So to be honest, many clinicians nowadays are actually very open to new technologies. In my experience, doctors and surgeons are increasingly coming to us as researchers with ideas and looking for collaborations involving robotics, automation, augmented reality, virtual reality, and AI-assisted systems, and also advanced imaging technologies. And there is a growing recognition that these tools can improve precision and support better outcomes for patients. Interestingly, I would say that patients are often more cautious than clinicians. When people hear the phrase autonomous robot surgery, they sometimes imagine a robot operating completely alone.
Yeah, they imagine like a humanoid robot walking in and doing the operation.
Exactly. And that's really not the case, right? So, for example, I was very impressed by how widely robotic surgery has been integrated into public hospitals in Italy and offered through the public healthcare system. That's amazing. And that's a major milestone, I think, because it shows growing trust and acceptance of robotic assisted procedures. In the UK, I personally feel we are still a little behind in terms of, large scale adoption and accessibility, but it's coming. And it's also important to clarify this, that today's robotic surgery system typically involve very low levels of autonomy, right? Most systems are teleoperated, meaning that the surgeon is fully in control the entire time. The robot doesn't make independent surgical decisions, and it acts as an advanced tool that can improve dexterity, precision, stability, and camera control in most of the times. So that said, autonomy in medical robotics is not simple, on or off.
Yeah.
There are actually different levels of autonomy. As we say, there is a lot of research and literature around this topic. And many current systems operate with high human supervision and low autonomy. But researchers nowadays are developing autonomous subtasks within the procedures. So we are trying to test small tasks in lab conditions, with higher autonomy using robotic systems in order, at some point to be able to test these small tasks in more realistic conditions and environments. But I think the key point is that the future of medical robotics is likely to be, collaborative rather than fully independent and fully autonomous. So the goal is, again, not to replace surgeons, but to augment human capabilities and try to enhance doctors and clinicians' abilities and combining, of course, human expertise, judgment, and decision-making with robotic precision and consistency.
Yeah, absolutely. Can you give one or two examples maybe of the kind of subtasks that would be good candidates for autonomy?
Exactly. So I would vote for the robot control of the needle injection, for example, system that I'm working on. So, for example, in one of my previous projects, we developed a handheld device that is able to perform this blood testing, in the arms, and especially for babies and kids cases where their veins are very fragile and they are difficult to be detected by a naked eye by the doctors. So in that cases, we have developed this handheld device that was equipped with a camera system and a mini display as well. And we could recognize real time using an infrared, near infrared camera, the veins during this procedure. So this standalone task is very helpful, I think. And we were able also to disconnect this from the handheld device, for example, and the device could be used independently of the vision system and vice versa. So these are two different tasks that combined can have a fantastic result, but also independently can be used in a safe way somehow. And at the same time, the needle insertion during the operation was also performed independently and autonomously, because we had used EBI sensor, as it's called, in bioimpedance sensor, that was able to detect the blood real time. So this is something that can be used independently and can reach a high autonomy level. I mean, because we trust the sensor somehow, and we trust that our system can have quite good results.
Yeah, that's really interesting. So you've also worked on robotic systems for autonomous assembly and also autonomous disassembly and kind of waste sorting and recycling. And this is an area I'm really interested in. I'm really hopeful that robotics can help improve sustainability in that way. Can you talk a bit about what this robot or robots look like and how it works?
Yeah, waste sorting is actually at the same time extremely challenging robotics problem, but quite impactful. So first of all, it can be quite challenging because of the environment that is very unstructured, very challenging, especially if you go, in big recycling centers. The conveyor belts, they are full of materials like recycling items. And we need to train robotic systems to be able to sort these items. but out of a very dense environment with many overlappings, dirty objects, like full of dust, deformed most of the times that you can hardly say what this object used to be before it ended up there. So that's quite big of a problem. And as I said, like objects come in different shapes, sizes, materials, and conditions, like very crushed cans, for example, plastic containers, and mixed materials, and with quite a lot of overlappings and hidden objects. So the systems we developed use robotic arms combined with computer vision and AI-based perception. And essentially, the robot looks at the waste stream using vision cameras and multispectral cameras sometimes in order to identify the objects and material also often, and then decide how to grasp it and how to sort them, because there are, different type of bins. And we want the plastics to go to the plastic bins, and especially in plastics, we have also subcategories like PPT and others. So we want the robotic system to be able to perform all these tasks. One of the challenges, as I mentioned, is that the environment is very unstructured, and we have a moving conveyor belt that constitute also different challenges in the system. And all the decision needs to be taken like real time and without lag and latency. The manipulation aspect is also quite difficult because, again, if you have like a multi-finger gripper and goes into this like mass of objects, it might not be able to separate one specific object and being able to grasp it. So most of the times we use vacuum systems and suction mechanism in order to grasp the specific object. So yes, in general, I think that it's a quite challenging area, but at the same time, there is quite a big of a progress, and there are quite a lot of companies that undertake this robotic sorting of waste nowadays. I used to work in Greece on a project that we were the first in Greece that we deployed the system in real recycling industrial partner. And it's a big thing, I think, that nowadays, there are even more companies that work on this in Greece, and it has quite considerable results, like facilitates a lot the process of sorting and facilitate the life of humans, I believe, because it's quite, hazardous environment for human to work on in terms of health and safety.
Yeah, definitely. So if you're training machine learning to identify the objects, how do you know that it's learning the right features? Because I can imagine it could learn, oh, this is a plastic bottle based on like the label, and then the company changes their branding and the machine learning algorithm can't identify it anymore. So you need it to pick up on like more important traits about what it's looking at, if you see what I mean.
Yeah, that's a very interesting question, to be honest. It's not a one shot, right? It's not that we are training a specific data set and then that's it. I mean, we have like the best results and we go on. There is, a continuous process and we feed our data sets all the time. I mean, usually we have also quite good and close partners from the industry, like recycling industries, that feed us with more data. So we are going there, we put our cameras, and we get continuously new data. So we train our models all the time, this never stops. And of course, we have metrics, quantitative metrics, that we can get the percentage of accuracy and repeatability of our data set. So we understand, this is a model that works well here. This is a model that doesn't work well for this. Because I didn't mention also that there are different type of recycling streams, right? There are plastics, there is also wood or construction waste. So, we need different type of data for all these different type of streams. And of course, if you go in different countries, you will see different type of waste, reflect a bit the market of its country, I would say.
Yeah, definitely. Yeah, it's a really interesting problem, but I'm glad that progress is being made.
Thanks.
Maria, it's been lovely talking to you today. I've been speaking to Maria Koskinopoulou from Heriot-Watt University. Thank you.
Thanks so much, Claire. Thanks.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And check out @Robot Talk Pod on social media to see a photo of a dual arm robotic system for disassembling hard drives, which Maria has been working on. I thought you might like to hear a sneak peek of the latest bonus episodes, which feature interviews from the European Robotics Forum earlier this year.
When we talked about reindustrialization of robotics within Europe, and what are some of the aspects and opportunities that we can see to sort of improve the situation in Europe with where parts come from and how we can take that opportunity to make Europe stronger.
We need to be thinking in a way that basically both protects our societies, provides us with value, and allows us to participate in the world, not be subject to the world.
So we come from communication sector, telecom, and understanding verticals, particularly robotic needs. It's one criteria for any researcher, for any developer to understand the requirement before making the solution development. So ERF is a very interesting and dynamic, rich platform to communicate and interact with the robotic experts. And
so now we are talking about 6G, potentials, capabilities, requirements. However, often we forget about the necessities. Why are we doing it? Is it just a technological gimmick? Is it just like an engineering fun? No, it's supposed to have a purpose, and the application is the purpose.
So these devices that you have here at the show have the ability to be able to remotely control robots. And we can do that in order to protect the operator from a toxic environment, or we can do that to protect the product so that it doesn't get contaminated.
It's called MonkeyBot because the idea came from seeing a monkey at the zoo climbing on a rope. I think it looks more like a caterpillar because it does this kind of like shrinking and expanding motion.
Yeah, kind of like inching along.
Yes.
The pipe, yeah.
So one gripper is always attached to the pipe and then the other stretch itself and holds.
If you'd like to hear more from ERF, sign up as a supporter on Patreon by going to patreon.com/Claire Asher. You'll get access to the full catalogue of bonus episodes, plus lots of other cool supporter perks. Next week, I'm talking to Edward Mayer from Machina Labs about robotic blacksmiths. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.